Hello, everybody. So, we haven't talked about something called a logistic function, and that's what this is right here. So, here is this specific one. I'm talking about the green function. Is this 10 divided by 1 plus 3 times zero point 0.4 raised to the x? So, it kind of behaves like an exponential, but it is not an exponential. You can't take zero point 0.4 to the x and then do a bunch of transformations and get this. It just it won't happen, but it's kind of related to it. But it's its own function. It is so this unit we have three functions: exponential, logarithmic, and then this logistic. And a couple things to recognize right off the bat. First of all, the domain. It goes forever to the left. It goes forever to the right. So the domain is always all real. But the range, this is called bounded. It has a border up top by a horizontal asymptote and a border at the bottom. So it is completely bounded. For this example, it's bounded between 0 and 10. And I think all the ones we're going to work with this chapter, it's always between 0 and some positive number. But it could be flipped upside down, so it could be between a negative number and 0. But 0 is always in there. It has a y-intercept, and it will not have an x-intercept unless it gets sunk down a little bit. So logistic functions are interesting how they play about in the real world. I used to have a fish tank, and fish, like many animals, they reproduce exponentially, right? But my fish tank can only hold 25 gallons. So my fish will procreate exponentially, but only to a certain point, right? I'm not going to end up having a million fish in my fish tank because the resources aren't there. There's only 25 gallons in the fish tank. So at some point, the fish will stop reproducing. So the fish will reproduce and the population will grow until a certain point, and then it'll taper off. And this is also like what's it called? The flu, the pandemic that's going on right now. So things like that, they will spread exponentially. They will spread exponentially, but not forever. I mean, if we do nothing about the coronavirus, look, if the coronavirus just keeps on going and going and going, it's not going to just skyrocket exponentially because eventually it's going to reach a maximum. I mean, if everybody in the world gets it, that's 7 billion people. So it can't get more than that, right? So at the very worst, 7 billion people, that would be the max. But it tends to taper off. So things grow exponentially up to a certain point, and then they taper off. What are we responsible for? Well, we'll come back to logistic functions in about a week or so when we solve. But for now, it's a matter of some basic things like find the two asymptotes and determine the end behavior, but without a calculator. So let's get some number sense going on here. So I just 1 plus 3 to the x. Let's just think about numbers. 1 plus 3 to the x equals what? Well, it depends on what x is. If x is 2, then 1 plus 3 to the 2 is 9. If x is 4, then that's 1 plus 81. That's 82. 3 to the 30, I have no idea what 3 to the 30 is, but it's huge. It's a huge, huge number. And 1 plus a huge, huge number is, I don't know, but it's very, very big. 3 to the 100 is even bigger. I mean, don't even know the words to describe how big that is. Plus 1 really doesn't matter. I mean, if you have $10 million and someone gives you one more dollar, that dollar doesn't really mean anything to you. So this 3 to the 100 is the dominant term here, and it just makes it huge, 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 huge. So what can I say about 1 plus 3x in general? I can say that when x gets big, so does the result. What about when x gets really small? So starting with 0, remember 3 to the 0 is 1, so 1 plus 1 is 2. 3 to the negative first is a third, so 1 plus a third is 1.3, repeating. 3 to the negative fourth is 1 over 81, so 1 plus 1 over 81 is 1.01234. 3 to the negative 10th is 1 over 3 to the 10th. And 1 plus 1 over 3 to the 10th is that in decimal form. 1 plus 1 over 3 to the 20th? Is that in decimal form? So what conclusion can you draw? When x gets really, really small, what is happening to the result of 1 plus 3 to the x? It's getting really, really close to 1. It's basically 1. The reason why is because 3 to a really small exponent is basically 0. And here's, let me elaborate on that just really quick. So 3 to the negative 100, that negative 100 is a pretty small number. That's the same thing as 1 over 3 to the 100th. And 3 to the power of 100 is 5.2 with 47 zeros after it. So that's just an incredibly large number. So 1 divided by 5.2 with 47 zeros after it is basically 0. Basically 0. That would be like having one pizza and separating it into all the atoms that are on the moon. And each atom would get basically nothing. So 1 divided by a huge, huge number is basically nothing. And this number sense is going to help us. This is going to help us mathematically. So 3 to the negative 100 is basically 0. Not exactly 0, but it basically is. So that therefore 1 plus something that's basically 0 is 1. Just like 5 plus something that's basically 0 is really just 5. Okay, so here is a logistic function. What happens when x gets really, really, really small? Well, we kind of thought about that one already. 1 plus 3x. When x got really, really small, it's basically 1 plus 0. So when x gets small, the denominator becomes 1 plus 0. So it just becomes 1. And 2 divided by 1 is 2. So as x approaches negative infinity, so in other words, when x gets really small, the function approaches 2. And that is written as a limit. It's this. The limit of f of x is 2 when x approaches negative infinity. What happens when x gets really, really big? Well, we saw that over here. When x gets really, really big, 1 plus a really, really, really big number is itself really, 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 really big. So as x gets big, you end up taking 2 divided by a really big number. So 2 divided by a really big number is basically 0. If you have 2 pizzas and you have to feed everybody on Earth, everybody still gets basically nothing because 2 divided by 7 billion is such a small number. It's not 0, but it's really darn close. It's basically 0. In math, we say it approaches 0. And that's the limit on the other side. The limit of the function as x approaches infinity is 0. And remember, the limit is what number the y value approaches when x gets closer to a certain number. All right, so here is yet another function, logistic function. Let's talk about the end behavior first. When x gets really small, so negative 100, let's say, what is 2 raised to the negative 100? It's basically the same thing as 3 raised to the negative 100. It's basically 0. Not exactly 0, but basically 0. So when x gets really, really small, this 2 to the x is basically 0. So now what's left over? It's 7 divided by 1 plus 0. So it's 7 divided by 1, which is 7. So when x gets really small, the y values approach 7. What happens when the x values get really big? Well, what's 2 to a really big number? It is itself a big number. 2 to the positive 100 is really, really big. And 1 plus a big number makes it even bigger. And 7 divided by a very large number is essentially 0. So here are the end behaviors. Remember what these things look like. They have a domain of all real numbers. But they eventually approach a horizontal asymptote to the left, and they approach a horizontal asymptote to the right. So this one, as I go to the left, it's approaching y equals 7. And as I'm going to the right, it's approaching y equals 0. Those are the two asymptotes, y equals 0 and y equals 7. The domain is all real, because the domain right now acting as an exponent, and we've already talked about this. Exponents can be anything. The range, however, it is bounded between 0 and 7. It does not include 0. It does not include 7, but it is bounded by that. So it's between 0 and 7. This one does not have an x-intercept. None of them do. None of them do, unless I transform this down. If I put a -2 right here, it would shift it down 2. Then it would have a x-intercept. Otherwise, it doesn't. The y-intercept. What's the y-intercept? It is always the result of plugging in 0 for x. So 7 divided by 1 plus 2 to the 0. Well, 2 to the 0 is 1. So this is really 7 divided by 1 plus 1. And 1 plus 1 is 2. 7 divided by 2 is 3.5. So that's the y-intercept. 0, 3.5. Now I can kind of graph it. I know the two horizontal asymptotes, 0 and 7. And I know the y-intercept. And I have some basic idea of what these things look like. And I know that to the left, when x gets small, to the left, it's approaching y equals 7. And to the right, when x approaches infinity, it's swooping down to y equals 0. And there you have it. Y-intercept of 3.5. When I go to the left, it's approaching 7. When I go to the right, it's approaching 0. And intervals of increasing, it's never increasing. As I move from left to right, it's never increasing, so that's really not available. It's always decreasing on its entire domain, and its entire domain happens to be all real numbers. Let's try again. To really participate here, I would pause the video and try to determine what are the two limits here. What number goes underneath these blue boxes? Okay, let's start with x approaching negative infinity. So this is 0.4 to the negative infinity. So when 0.4 gets raised to a really small number, let's actually do the when x gets bigger first. When x gets bigger, 0.4, please notice that 0.4 is the same thing as 4/10. So this is our number sense. Are we strong or weak here? When x gets big, just think about 4/10. What is 4/10 to like the 50th power? Is it a really big number or is it a really small number? 4/10 to a big power like 50. On the calculator, I did 4/10 times 4/10. As a decimal, it's 0.16. I took 4/10 times 4/10 times 4/10, 0.064. So it's getting a little bit smaller. 4/10 is 40%. So when you multiply these two, this means you're taking 40% of 40%, and that's 16%. And then here you're taking 40% of this, which was 16%. So what's 40% of 16%? It's even smaller. It's 0.064. So 0.4 times 0.4 times 0.4 times 0.4 is this. And I got a little impatient, and I just did 0.4 times 0.4 times 0.4 times 0.4 to the 17 more times. And you see how small this number is. So it's 0.0000, so 8 zeros, and then 4, 3, 9, 8, etc. So it's basically 0. 4/10 to a really large number, like let's say 200. Whoops. Oh, what happened here? Oh my gosh, I forgot to. This is the fraction. So let me you put a decimal with Inspire. If you put a decimal in your problem, it'll convert it to a decimal. Okay, so 4/10 to the 200th power is you move this decimal to the left 80 spots, so 79 zeros, and then 258. So I hope you're convinced that it's basically 0. When x approaches infinity, 4/10 will become 0. 0.4 will become 0. So you have 10 divided by 1 plus 3 times 0, which is 10 divided by 1. So the y values approach 10, because 10 divided by 1 is 10. Negative infinity, well, when x is a negative number, like negative 200, the negative would flip this around, making it 10 fourths. And when you take 10 fourths and multiply it by itself, it gets really, really big. With all these problems, the exponential part is either going to get really, really big to infinity or really, really close to 0. That's always going to happen. So this, when x itself got big, this went to 0. So that means the other one is going to go to infinity. When x approaches negative infinity, this 4/10 gets really large. And 10 divided by a really large number is 0, essentially 0. And those are the two horizontal asymptotes. The domain is all real. The range is from 0 to 10. There is no x-intercept as usual. But what is the y-intercept? Again, plug in 0 for x. 0.4 to the 0 is 1. So this is 10 divided by 1 plus 3 times 1, which is 10 divided by 4, which is 2.5. So the y-intercept is 0, 2.5. And now I can graph it. I know the y-intercept, so I would plot the y-intercept. I know that when I go to the right, it's curving up towards y equals 10, approaching y equals 10. When it goes to the left, it's curving down towards y equals 0. So it looks like this. And it's always increasing along its entire domain, so all real, and it's never decreasing. All right, 3 more examples, and then we're going to stop. So here, E is just a number, 2.7. It's irrational, it goes on forever, but it begins with 2.7. Well, what happens when x gets really, really small, like negative 100? Well, e to the negative 100 would basically just be 0. So this is 3 divided by 2 plus 5 times 0, which is 3 divided by 2, so it's 3 halves. So again, when x gets small, this e becomes 0. And when x gets big, well, when x gets really, really large, like e to the 100th, this would become very, very, very large. So 3 divided by 2 plus 5 times a big, big number makes the whole denominator big. And 3 divided by a big number is 0. Remember, 3 divided by any number divided by a much, much larger number will always be 0. Here, 1 divided by 3 to the 100th is 0. But even if I replaced 1 with like 5,000, 3 to the 100th completely overpowers 5,000. It would still be 0. You're dividing by such a huge number, it's essentially 0. And then if you have your end behavior, you've got your asymptotes. The y-intercept. So when x is 0, what's the result? When x is 0, this e to the 0 becomes 1. So it's 3 divided by 2 plus 5 times 1, which is 3 divided by 7. Here, when x, okay, so here this is different. Our base is a 1/2. And please realize that I could just make that a 2. I could flip it as long as I change the sign of my exponent. So if x becomes negative x, then 1/2 will become 2. Now what happens when x gets really, really small? Well, let's plug that into here. Because when x gets really, really small, the negative x value, like negative 100, will cancel out with this negative. And so it'll end up being 2 to like the 100th power. And that's a big, big number. So 6 divided by a big number is 0. When x gets really, really large, like this one might be easier to think about. When x gets large, like when x is 100, well, what's a half times itself 100 times? That's basically 0. Taking a half of a half of a half of a half 100 times, you basically have nothing. So when x approaches infinity, 1/2 to the infinity will be 0, essentially 0. So 6 divided by 1 plus 0 is just 6 divided by 1, which is 6. And you see how the common thing with all these, one of them is 0 and the other one is some other number. It's usually the number that's attached right here. So 3 divided by 2, that's the other one. Here, one of them is 0 and the other one is 10. It's 10 divided by 1. Here, one of them is 0, the other one was 7, because 7 divided by 1. And once you have the end behavior, you've got the asymptotes. What about the y-intercept? When x is 0, 1/2 becomes 1. So 6 divided by 1 plus 2 times 1 is 6 divided by 3, which is 2. And last, if you're given this negative exponent, always realize you could change it to a positive exponent just by flipping that base, just by making it 1 over e. So when x approaches negative infinity, I'll plug it into here. Like when x is negative 100, the negative with the 100 cancels out with this negative, making it positive 100. So e to the positive 100 is really big, and 3 divided by a big number is 0. So in this direction, e became infinity. That means in the other way, e is going to go to 0, which it does. When x gets really, really big, 1 over e to a really big number is basically 0. So 3 divided by 2 plus 0 is 3 divided by 2, which is 3/2. And the asymptotes are y equals 0 and y equals 3/2. The y-intercept, if x equals 0, this is 5 times 1. And 3 divided by 2 plus 5 is 3/7 again.